Every morning, from almost every place on Earth, the sun rises. It climbs through the sky with the unhurried reliability of something that has been doing this for 4.5 billion years. We see its face, the broad, luminous disk that warms the ground and drives the weather, and makes photosynthesis possible and gives the sky its blue. We have been watching this face since before we had language to describe it. Civilization that has oriented itself around the daily passage of this light. And yet, there are two regions of the sun that no human eye has ever seen clearly. Two areas that sit directly above and below the star's rotational axis. The north and south poles of the sun that have remained for virtually the entire history of solar observation, obscured not by clouds of distance, but by geometry. By the simple, fundamental fact that we live in the same plane as the sun's equator, and that looking at a pole from the equatorial plane is like trying to see the top of your head by looking straight ahead. For centuries, solar astronomers studied the sun's face and described it with increasing precision. Sunspots, mapped since Galileo. The corona, revealed during eclipses. The chromosphere, the photosphere, the complex magnetic structures visible in filtered light. The solar cycle, its 11-year rhythm of activity and quiet. All of this knowledge, accumulated with patience and ingenuity, describes the sun's equatorial face. The poles remained a mystery, completely unknown then. We could infer things about them, model them, make predictions based on what we understood of the physics, but we could not see them directly. Not the way you see something when you look at it squarely, and let the light fall on the instruments without the compression and distortion that oblique angles impose. Then, in February 2020, spacecraft launched from Cape Canaveral on a trajectory unlike any solar mission before it. Not aimed at the sun's equatorial plane, not designed to orbit in the ecliptic. The flat disk of the solar system that defines the orbits of all the planets and the paths of virtually all previous spacecraft. This mission, the European Space Agency's solar orbiter, was designed from the beginning to climb, to use the gravity of Venus, counted repeatedly, to tilt its orbit progressively away from the solar equatorial plane, to look down, and eventually up, at the regions of our star that had never been properly observed, and what it has returned. In images, in magnetic field measurements, plasma data, and coronagraph frames and extreme ultraviolet spectroscopy, has been genuinely surprising. Not in every respect. Physics of a star's poles is not completely alien from what was expected, but in specific, measurable, scientifically significant ways, the sun above and below its equator is more complex, more structured, and more interesting than the models predicted. Tonight, we explore those regions. We explore what sits directly above and below the fire that sustains us. We trace the history of how we came to study the solar poles, what the instruments have found there, what those findings tell us about the nature of our star, the solar wind that flows through the entire solar system, and the magnetic cycle that governs space weather across the planetary family we inhabit. This is a story about seeing something clearly for the first time, about the particular kind of scientific satisfaction that comes when an instrument finally pointed at the right place, and the data returns something that rewards the patience and the engineering with genuine, interesting surprise. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. The reason that the solar poles remained poorly observed for so long is not a failure of ingenuity or ambition. Tahax. It is a consequence of one of the most fundamental architectural features of the solar system. Planet in the solar system orbits the Sun in approximately the same plane. Mercury, Venus, Earth, Mars, Jupiter, all of them trace paths around the Sun that are tilted by at most a few degrees from a common flat disk. This disk, the plane of the solar system, is called the ecliptic. It is a relic of the formation of the solar system itself, the original rotating cloud of gas and dust from which the Sun and planets formed was flattened by its own rotation into a disk, and the planets condensed from that disk and have been orbiting within it ever since. From within the ecliptic, observing the Sun's poles is geometrically difficult. The north pole of the Sun, the point directly above the rotational axis, is visible from the ecliptic plane only at a very oblique angle. When you observe a feature at the Sun's north pole from Earth's position in the ecliptic, you are looking at it from nearly 90 degrees away from its true position. The pole is compressed, foreshortened, seen almost edge-on. The features there are stretched and distorted by perspective. The spectroscopic measurements, particularly the Doppler velocity measurements that reveal how plasma is moving on the solar surface, are degraded because the polar regions move almost entirely along the line of sight, rather than across it, producing very small Doppler shifts that are hard to measure accurately. The Sun's rotational axis is also not perfectly perpendicular to the ecliptic. It is tilted approximately 7.25 degrees relative to the normal of the ecliptic plane. This tilt means that for about 6 months of each year, Earth's vantage point allows a slightly better view of one solar pole or the other. A tilt toward the north in September, toward the south in March. But 7 degrees is a very small tilt. It improves the view modestly. It does not solve the fundamental problem of trying to observe a polar region from an equatorial vantage point. Escape from the ecliptic is energetically expensive. The solar system's angular momentum is overwhelmingly concentrated in the ecliptic plane, changing the inclination of an orbit. Moving from the equatorial plane toward a polar plane requires enormous energy expenditure. To send a spacecraft into a truly polar orbit around the Sun, simply providing enough energy to reach the Sun is not sufficient. The spacecraft must also change its orbital inclination by nearly 90 degrees, a velocity change that exceeds the capability of any rocket currently in operation. The ingenious solution, used by the Ulysses mission in the 1990s and refined significantly by Solar Orbiter, is to use the gravity of Jupiter or Venus as a slingshot. By flying close to a large planet and using its gravity to redirect the spacecraft's trajectory, mission can achieve orbital inclinations impossible through rocket propulsion alone. Ulysses used Jupiter's gravity to swing into a polar solar orbit. Solar Orbiter uses repeated Venus gravity assists, each flyby tilting the orbit by a few degrees, to progressively raise its orbital inclination over the course of several years. This progressive inclination increase is patient science. Solar Orbiter's first Venus gravity assist in 2020 gave it a modest inclination. Subsequent flybys have raised it further. By the late 2020s, the spacecraft will observe the Sun from latitudes above 30 degrees, the highest inclination of any solar imaging mission in history, with the best direct views of the polar regions ever achieved. Understanding why this geometry was the obstacle allows us to appreciate why the results, when they arrive, are so genuinely informative. The scientific interest in the solar poles predates solar orbiter by more than half a century. The recognition that the poles played a special role in the Sun's magnetic cycle, and that observing them directly would be enormously valuable, dates to the earliest days of systematic solar magnetism research. The Babcock-Layton model of the solar cycle, developed in the 1960s, placed the polar magnetic fields at the centre of the cycle's dynamics. In this model, which remains the foundation of modern understanding of the solar cycle, the magnetic field of the Sun behaves something like a conveyor belt. Active regions emerge at mid-latitudes and produce sunspot pairs with opposite magnetic polarities. Over the course of the solar cycle, large-scale surface flows, called meridional flows, carry magnetic flux from the active regions toward the poles. This flux accumulates at the poles, eventually cancelling and reversing the polar fields, which then serve as the seed for the next cycle's activity. Polar fields are, in this model, the memory of the solar cycle. They carry forward the information from one cycle to the next, strength at solar minimum. The quiet period between cycles is the primary predictor of the amplitude of the following solar maximum. Understanding the polar fields is therefore essential for predicting the level of solar activity and the space weather it drives years in advance. Observing the polar fields from the ecliptic plane is like measuring them through frosted glass. The line-of-sight magnetic field measurements available from Earth-based magnetographs or from spacecraft in the ecliptic suffer from the projection effects we have already discussed. The polar magnetic field strength is systematically underestimated when measured from the ecliptic, perhaps significantly, because the field components perpendicular to the line of sight are not captured. The Ulysses mission, launched in 1990 and arriving at high solar latitudes in the mid-1990s, was the first spacecraft to directly sample the environment above the solar poles. Ulysses was primarily an in situ mission. It measured particles and fields in the space above the poles rather than imaging the solar surface. Its magnetometer, plasma analyzer, and energetic particle instruments provided the first direct measurements of the solar wind above the poles, revealing, crucially, that the wind above the polar regions is faster and smoother than the wind from the equatorial regions. The polar wind streams at approximately 700 to 800 kilometers per second, in contrast to the slower, more variable 3 to 500 kilometers per second typical of the equatorial wind. This discovery, the fast polar wind, was one of the most important results of Ulysses. But Ulysses was too far from the Sun, and its instruments not designed for imaging, to reveal the polar surface itself. The solar surface at the poles remained unseen. The Solar Dynamics Observatory, launched in 2010 and operating from a geosynchronous orbit around Earth, provided extraordinary imaging of the Sun's full disk at multiple wavelengths in extreme ultraviolet and visible light, but it orbits in the ecliptic, and therefore sees the poles only at the same oblique angle available from Earth. Its magnificent images have transformed our understanding of solar dynamics in the equatorial regions and at mid-latitudes, but the poles remain in penumbra of its coverage. It was into this waiting space, this region of known ignorance, recognised and documented and theorised about for 50 years, but never directly resolved, that Solar Orbiter was sent. When Solar Orbiter began returning its first images from elevated solar latitudes in the early 2020 us, still not at the ultimate planned inclinations, but already tilted enough to see the poles more directly than any previous imaging instrument. The science teams examined the data with a careful combination of preparation and genuine openness to surprise. They had models, they had decades of theoretical work on what the polar regions should look like. They had the in situ measurements from Ulysses, and from the earlier portions of Solar Orbiter's own orbit to constrain the physical conditions above poles. They had expectations, and the data, in important ways, exceeded and deviated from those expectations in ways that have generated substantial scientific discussion. The most immediate and visually striking finding from Solar Orbiter's early imaging was the discovery of what the science team named campfires, small, short-lived brightening events detected in extreme ultraviolet images scattered across the solar surface, including at higher latitudes. These campfires, ranging in size from a few hundred to a few thousand kilometers, appear to be miniaturized versions of the solar flares and eruptions that are familiar from images of active regions. They were too small to be detected by previous instruments, which lacked Solar Orbiter's combination of proximity and resolution. Campfires are thought to be evidence of magnetic reconnection events. The process by which our oppositely directed magnetic field lines snap together, releasing stored magnetic energy as heat and particle acceleration. On the Sun's equatorial face, reconnection events of all sizes are known to occur. What the campfires revealed was that this process also occurs ubiquitously in quieter regions, including the polar regions, and at scales far smaller than previously detected. This has significance for one of solar physics' most long-standing mysteries, the coronal heating problem. The Sun's corona, its outer atmosphere, is millions of degrees hotter than the visible surface below it. Simple thermodynamics says this is backward. Temperatures should decrease as you move away from a heat source. Something is heating the corona, and that something must be depositing energy higher in the atmosphere rather than below it. Leading candidate has long been the dissipation of magnetic waves and small-scale reconnection events. The campfires observed in abundance support the idea that ubiquitous small reconnection events contribute significantly to coronal heating, and the evidence that this occurs at polar latitudes as well as at the equator is a genuine refinement of the coronal heating picture. The magnetic field of the Sun's polar regions has been the subject of theoretical modelling and indirect observation for more than half a century. What Solar Orbiter's direct observations are revealing is a picture that is simultaneously broadly consistent with those models and specifically more complex in ways that matter for understanding the solar cycle. The broad picture is this: during solar minimum, the quiet period between cycles, the Sun's magnetic field is most organized. The equatorial regions have weak, mixed polarity fields. The polar regions carry strong, coherent, unipolar magnetic flux. Predominantly one polarity at the North Pole, the opposite polarity at the South Pole, like a tilted bar magnet, aligned roughly with the rotation axis. This large-scale structure is what the models predicted, and Solar Orbiter's measurements, as its orbital inclination has increased, have confirmed that this structure is present. The polar fields are organized. They are approximately unipolar at large scales, but the fine-scale structure, what the field looks like at the scale of individual magnetic features rather than the global average, is considerably more complex. The polar field is not a smooth, uniform background. It is composed of numerous small magnetic concentrations, bundles of field lines with strengths of several hundred to a few thousand Gauss, organized at scales of tens to hundreds of kilometers, interspersed with regions of weaker, more mixed polarity field. These small concentrations are called magnetic bright points or small-scale magnetic elements, and their detailed properties and distribution near the poles had not been well characterized before Solar Orbiter. The instrument that reveals them is the polarimetric and helioseismic imager, known as PI, a sophisticated magnetograph designed specifically to measure the magnetic field across the solar surface with high resolution. PHI's measurements at high latitudes, achieved as Solar Orbiter's inclination has increased, have revealed that the polar field is organized on small scales into discrete concentrations that are separated by regions of weaker field. Total magnetic flux at the poles, the sum of all these individual concentrations, is larger than previous measurements from the ecliptic had suggested. The projection effects of ecliptic observation had systematically underestimated the polar field strength. This has practical consequences. The strength of the polar fields at solar minimum is the primary predictor for the amplitude of the next solar cycle. Previous predictions of cycle amplitude, including the predictions made for solar cycle 25, which began in December 2019, were based on underestimated polar field measurements from the ecliptic. Solar Orbiter's direct polar measurements they accumulate will provide significantly improved polar field measurements that should improve the accuracy of future cycle predictions. But the surprise is not merely in the total field strength. It is in the fine-scale structure. Polar fields are not as smooth as the simplest models suggest. They have spatial complexity at small scales that the models do not fully capture. Understanding this complexity, and its implications for the transport of magnetic flux to the poles over the course of the solar cycle, is an active and genuinely productive area of current solar research. Among the most significant findings emerging from Solar Orbiter's high-latitude observations is the detection of organized, large-scale circulation patterns near the solar poles. Circulation that appears to be considerably more structured than the simple poleward drift of magnetic flux assumed in the most basic versions of the flux transport model. On Earth, polar vortex is a familiar concept, a large-scale atmospheric circulation pattern that forms at the polar regions and influences weather systems across vast distances. The Sun's polar regions, it is becoming apparent, host an analogous kind of organized circulation, though governed by the physics of plasma and magnetic fields rather than the fluid dynamics of atmospheric gases. The Solar Orbiter mission's ability to observe the solar surface from progressively higher latitudes, measuring Doppler velocities, and tracking the motion of surface features, has provided the first direct evidence for the velocity field near the solar poles. What the data reveals is that the plasma near the poles is not merely drifting gently poleward in a smooth, symmetric flow. It is organized into structures, flows that rotate relative to the background rotation of the Sun, flows that show evidence of vortex-like character. This finding connects to a broader question in solar physics about what drives the differential rotation of the Sun. The fact that the equatorial regions rotate faster than the polar regions. The transition in rotation rate from the mid-latitudes to the poles is not smooth and gradual. It involves complex dynamics in which convective flows, magnetic torques, and the angular momentum transport of the meridional circulation all play roles. Polar vortex, or polar vortex-like structure, observed by solar orbiter, represents an unorganized expression of these complex dynamics at the very highest latitudes. Its presence means that the polar circulation is not simply the passive endpoint of a poleward flow, but an active, structured dynamical region that influences how magnetic flux is processed and distributed near the axis. The implications for the solar cycle are real. If the polar field evolution is influenced by organized vortex circulation rather than simple poleward drift, the models of cycle-to-cycle prediction that depend on accurate polar field transport need to incorporate this complexity. The simplest models, which assume a smooth, symmetric poleward flow, may systematically misrepresent the actual dynamics. Polar regions of the Sun are dominated, during periods of low solar activity, by large persistent coronal holes. These are regions where the magnetic field is open, extending outward into interplanetary space, rather than looping back to the solar surface in the closed structures that characterize the more active equatorial regions. The distinction between open and closed magnetic field is fundamental to understanding how the Sun interacts with the solar system. Closed field lines trap plasma in the corona, producing the bright, hot, visible structures of active regions and quiet Sun loops. Open field lines allow plasma to escape. They are the source regions of the solar wind. The corona above open field regions is dark in extreme ultraviolet images, because the plasma density there is lower, producing the characteristic appearance of coronal holes. As dark regions against the brighter closed field corona, polar coronal holes are particularly significant because they are the source of the fast solar wind. The high-speed stream of particles that flows outward from the poles at approximately 700 to 800 kilometers per second. This fast wind, measured directly by Ulysses in the 1990s above both poles, is faster, smoother, and more uniform than the slow wind from the equatorial regions. The fast wind's origin in the open magnetic flux of polar coronal holes has been understood in broad terms for decades. But the details of how the wind is accelerated, how the plasma transitions from nearly stationary coronal material to 700 kilometers per second outflow, remain incompletely understood. Solar orbiter's combination of imaging and in situ measurements, the ability to image the polar surface, while also measuring the wind properties in situ as the spacecraft moves closer to the Sun and at higher latitudes, provides new data on this acceleration. What Solar Orbiter has found is that the fast wind from polar coronal holes carries embedded structures, small-scale velocity, and magnetic field fluctuations that trace back to processes occurring on the solar surface. The switchbacks observed by Parker Solar Probe in the inner heliosphere. Sudden reversals of the magnetic field direction within the solar wind appear to be preferentially associated with the fast wind from polar coronal holes, suggesting they are launched from the polar source regions. Polar coronal holes also evolve over the solar cycle. At solar minimum, they are large, centered on the poles, and clearly defined. As the cycle progresses towards solar maximum, and the polar fields weaken and reverse, the polar holes shrink, fragment, and eventually disappear, replaced by a disordered, complex arrangement of smaller holes and active regions that characterizes the maximum phase. The subsequent minimum, new polar holes form with reversed polarity, and the fast polar wind resumes. Solar Orbiter is observing through the early phases of solar cycle 25, following through solar maximum and into the subsequent minimum, and is providing the first direct polar observations across a complete transition of the polar field structure. This is genuinely new science, the solar wind that flows outward from the polar coronal holes. The fast wind that Solar Orbiter and Parker Solar Probe are now characterizing in precedented detail does not stop at the edge of the Sun's atmosphere. It fills the entire solar system and beyond. The region of space dominated by the solar wind, bounded by the pressure balance between the outer-flowing solar wind and the interstellar medium, is called the heliosphere. It is, in a very real sense, a bubble blown by the Sun in the surrounding interstellar space. Within the heliosphere, the Sun's magnetic field, carried outward by the solar wind, permeates all of space. Planets and their magnetospheres all exist within this solar bubble. The heliosphere extends to a boundary called the heliopause, the surface at which the ram pressure of the solar wind is balanced by the pressure of the interstellar medium. This boundary lies at approximately 100 to 120 astronomical units from the Sun in most directions. The heliosphere's shape is not spherical. It is elongated by the motion of the solar system through the interstellar medium. The Sun moves at approximately 320 kilometers per second relative to the local interstellar medium, producing a nose-on direction of compression and a downstream tail. The fast polar wind plays a specific role in the heliosphere's structure because it flows faster and carries more momentum per unit of stream area than the equatorial slow wind. It inflates the polar regions of the heliosphere more effectively. The heliosphere is wider in the polar directions than it might be if only the equatorial wind existed. The interaction between the fast polar wind and the slow equatorial wind produces a region at mid-latitudes called the rotating interaction region, where the fast polar wind flowing outward takes the slower equatorial wind from earlier in the solar rotation and piles into it, producing compression and rarefaction regions that rotate with the Sun. These structures, called CRs, are a significant source of enhanced particle flux in the heliosphere, affecting spacecraft operations, influencing cosmic ray modulation, contributing to the space weather environment. Understanding the polar wind, its speed, its composition, its embedded structures, processes that accelerate it, is therefore not merely an academic exercise in solar physics. It is directly relevant to the heliosphere's overall structure and to the space weather environment within which all the solar system's objects orbit and all human space activities are conducted. Imagine travelling outward from the Sun in the direction of its north pole, not in the ecliptic plane, the planet's orbit, but perpendicular to it, along the rotation axis, straight up. As you depart from the vicinity of the Sun, pass through the corona. At the poles, the corona looks different from the equatorial corona. There are no helmet streamers. The large, bright coronal structures produced by closed magnetic field lines that dominate the equatorial corona and extend outward as the heliospheric current sheet. Instead, the polar corona is characterized by polar plumes, elongated, ray-like structures of denser plasma extending outward along the open magnetic field lines of the polar coronal hole, and by the generally darker, more open appearance of the coronal hole itself. The polar plumes are one of the most visually distinctive features of the polar solar corona. They are visible in coronagraph images as bright radial structures extending outward from near the poles, typically rooted in concentrations of magnetic flux on the polar surface. Their plasma flows outward along the open field lines, contributing to the fast solar wind. As you continue outward past the corona, into the region called the inner heliosphere, you enter the domain of the fast solar wind. Moving along the rotation axis, you experience the cleanest, pristine version of this wind. The stream that has flowed directly from the polar coronal hole. Without mixing with the equatorial slow wind, it moves outward at 700 or 800 kilometers per second, carrying embedded magnetic field fluctuations and the switchback structures that Parker Solar Probes has measured in the inner heliosphere. The magnetic field structure along the polar axis is simpler than in the equatorial plane. The equatorial heliosphere contains the heliospheric current sheet, a wavy, roughly equatorial surface that separates regions of opposite magnetic polarity in the solar wind. The polar wind, flowing well above and below the current sheet, does not cross it and experiences a more coherent, single polarity magnetic field. Continuing outward past the planet's orbits, past Jupiter, Saturn, Uranus, Neptune, you reach the outer heliosphere. Here, the solar wind has been flowing for years since leaving the Sun. It has interacted with the interstellar medium through a region of deceleration called the termination shock, crossed the boundary between freely flowing solar wind and compressed subsonic wind, called the heliosheath, and is approaching the heliopause where the Sun's influence ends on South. The termination shock was crossed by Voyager 1 in 2004, approximately 94 astronomical units, and by Voyager 2 in 2007 at approximately 84 astronomical units. Interestingly, Voyager 1, which crossed above the ecliptic plane as it travelled outward, encountered the termination shock at a different distance than Voyager 2, providing evidence that the heliosphere is not symmetric above and below the ecliptic polar heliosphere. The regions directly above and below the Sun extends further from the Sun in some directions than in others, reflecting the complex three-dimensional shape of the boundary between the solar wind and the interstellar medium. Directly above and below the Sun, a distance of approximately 100 to 120 astronomical units, the heliopause marks the end of the Sun's direct influence. Beyond it, the interstellar medium, the thin gas and magnetic field of the galaxy between the stars, takes over. This, ultimately, is what lies directly above and below the Sun, at the greatest scale. The polar heliosphere, a vast, invisible tunnel of fast solar wind, extending from the polar coronal holes outward for 100 times the Earth-Sun distance, connecting the most intimate structures of the solar surface to the interstellar medium where the Sun story blends into the larger story of the galaxy. Heliosphere does not exist in isolation. It exists within a specific region of the Milky Way galaxy, a region that has its own physical character, its own gas density and magnetic field and particle environment, and the properties of that environment determine the size and shape of heliosphere and influence the conditions within it. Our solar system currently resides within a structure called the local bubble, a cavity in the interstellar medium approximately 300 light-years across, carved out by supernova explosions within the past few tens of millions of years. The local bubble is filled with hot, low-density gas, far less dense than the typical interstellar medium, and it is within this relatively tenuous environment that the heliosphere inflates. The low density of the local bubble gas means that the heliosphere is relatively large. The low ram pressure of the surrounding medium allows the solar wind to push outward further before being stopped. Denser interstellar medium, closer to a molecular cloud, for example, or in the denser mid-plane of a spiral arm, the heliosphere would be compressed to a much smaller size, potentially bringing the heliopause inside the orbit of some of the outer planets. Properties of the local interstellar medium are directly relevant to what lies above and below the Sun, because it is this medium that presses against the polar heliopause. The pressure balance between the outflowing polar solar wind and the incoming interstellar medium determines where precisely the polar heliopause sits. Measurements of the interstellar medium's magnetic field, using data from the Voyager spacecraft and from ground-based observations of interstellar absorption lines, indicate that the local interstellar magnetic field is not aligned with the ecliptic plane. It is tilted, roughly perpendicular to the galactic plane in some analyses. This misalignment between the interstellar magnetic field and the solar system's ecliptic plane contributes to the asymmetry of the heliosphere. The fact that it is not simply elongated in the direction of the Sun's motion, but shaped in a more complex way by the interaction between the flowing interstellar medium and the solar magnetic field it carries. Polar regions of the heliosphere, directly above and below the Sun, are therefore the regions where this interaction is most direct. The fast polar solar wind flowing outward along the polar axis impinges most directly on the interstellar medium in the polar directions, creating a heliosheath that is thinner and differently structured above and below than in the equatorial plane. What the Voyager spacecraft have measured at their positions, though they are in different directions, not directly above and below the Sun, is beginning to reveal the complexity of this boundary. The two Voyagers are sampling different portions of the heliosheath and providing data that constrains the three-dimensional structure of the heliosphere. The picture emerging is one of a heliosphere that is more complex and more asymmetric than the simplest spherical models suggested, and polar regions sitting above and below the Sun, where the fast wind and the interstellar medium most directly confront each other, are among the most important and least understood portions of that boundary. We have noted the importance of the polar magnetic fields for the solar cycle, the 11-year rhythm of solar activity that governs space weather across the solar system. Now let us trace that connection in more detail, because understanding it is essential for appreciating why the direct polar observations of Solar Orbiter are scientifically important beyond the immediate interest of seeing the poles for the first time. The solar magnetic cycle begins in the flux transport model polar fields at solar minimum. These fields, the accumulated organized magnetic flux that has drifted poleward from active regions in the previous cycle, are the seed of the next cycle. Their strength at minimum determines the field strength at the base of the convection zone, which determines how powerfully the differential rotation will wind up and amplify the field as the new cycle proceeds, which determines how many active regions will emerge and how large the eventual solar maximum will be. This chain of causation, from polar field strength at minimum to maximum activity level years later, is the basis for predictions of solar cycle amplitude. The method works as follows. Measure the polar field strength at solar minimum. Use a calibrated model to predict how that field will evolve into the next cycle, produce a prediction for the cycle maximum that will arrive approximately 5 years later. This method has had some successes, notably prediction by several research groups that solar cycle 24 would be weak, made at or near the minimum of cycle 23. Solar cycle 24 was indeed one of the weakest cycles in a century. But the method has also had failures. Prediction for solar cycle 25. The current cycle was for a moderate to weak cycle. Solar cycle 25 has exceeded predictions, activity running significantly above the forecast levels. The most likely explanation for this failure is that the polar field measurements on which the prediction was based were systematically underestimated. Because they were made from the ecliptic plane, subject to the projection effects that compress and distort the polar view. If the actual polar field strength was higher than the projected measurements indicated, the cycle amplitude prediction based on those measurements would be too low. Solar orbiters' direct polar field measurements, which avoid the projection problem by observing from higher latitudes, will provide the most accurate polar field data ever collected. Applied to future cycle predictions, they should improve the predictive skill of the flux transport model, but they have also revealed that the polar field is more complex than the simple, smooth structure that models assume. The fine-scale structure, vortex-like circulation, the spatial complexity of the magnetic concentrations. These features, not captured in the models, may be responsible for some of the remaining predictive errors. Incorporating them into improved cycle prediction models is a research goal that solar orbiters' data is directly enabling. The most dramatic event in the life of the solar poles occurs at solar maximum, the peak of each 11-year cycle, when the polar fields reverse. What was the north magnetic pole becomes the south. What was the south becomes the north. The entire global dipole of the Sun flips. This reversal does not happen instantaneously. It is a gradual process that unfolds over approximately a year or two, centered on the solar maximum. The polar fields, which were strong and coherent at the preceding minimum, weaken as active region flux is transported poleward and cancels the existing field. First, the field weakens to near zero, a period called polar field reversal, when the poles have essentially no net magnetic flux. Then, as new active region flux with opposite polarity continues to arrive and build up, polar field reverses sign and strengthens again toward the next minimum. The reversal does not happen simultaneously at both poles. North and south polar fields have historically reversed at different times within a solar maximum, sometimes separated by a year or more. This asymmetry between the northern and southern solar hemispheres in their cycle timing is a persistent feature of solar activity, observed across multiple cycles, and is not fully explained by the models. Observing the polar field reversal directly from the elevated vantage of solar orbiter provides, for the first time, ground truth view of this fundamental solar event. The PHII magnetograph on solar orbiter can measure the actual flux distribution at the poles as reversal proceeds, tracking how the old polarity flux cancels and the new polarity flux builds up. Spatial resolution and accuracy unavailable from the ecliptic. Solar orbiter is currently observing through the maximum of solar cycle 25, which is expected to occur in the 2024 to 2026 timeframe. And its polar observations during this period represent the first opportunity to directly observe a solar polar field reversal from high latitudes. The science of the polar reversal has implications far beyond the poles themselves. The reversal marks the transition of the solar cycle from its ascending to descending phase. It is the moment at which the Sun's global magnetic orientation switches, affecting the structure of the heliospheric current sheet, the modulation of cosmic rays entering the heliosphere, and the long-term space weather environment throughout the solar system. Getting an accurate, direct measurement of how the polar reversal actually proceeds, its timing, its spatial structure, the rate at which flux cancels and builds, will provide crucial data for improving the models of the solar cycle that underpin space weather prediction. The solar poles and the solar cycle they govern are not merely academic subjects for solar physicists. They have direct and increasingly important practical consequences for modern technological civilization. Space weather. The variation in the Sun's energy output, the acceleration of energetic particles, the distortion of Earth's magnetic field by the solar wind, affects virtually every aspect of human technological infrastructure that operates in or near space, or that depends on radio communications through the ionosphere. Satellite operations are affected by the enhanced radiation environment during solar maximum. High energy particles from solar flares and coronal mass ejections can damage satellite electronics, degrade solar panels, force satellite operators to place spacecraft in protective safe modes. The International Space Station's radiation exposure is significantly higher during solar maximum than during minimum, affecting crew health and requiring careful monitoring. GPS and navigation signals are affected by solar activity through the ionosphere. The layer, Earth's upper atmosphere, ionized by solar extreme ultraviolet and X-ray radiation. During solar flares, the ionosphere is rapidly ionized at a higher than normal rate, causing GPS signals to be absorbed or refracted. During geomagnetic storms, driven by coronal mass ejections that disturb Earth's magnetic field, the ionosphere is disturbed and turbulent, causing GPS positioning errors that affect aviation, maritime navigation, precision agriculture, and emergency services. Power grids are affected by severe geomagnetic storms through geomagnetically induced currents. Electrical currents induced in long conductor systems by the rapid changes in Earth's magnetic field. The 1989 Quebec blackout, which left 6 million people without power for 9 hours, caused by a geomagnetic storm produced by a major coronal mass ejection. The economic losses from a major grid event could, according to some analyses, rival or exceed those of a major natural disaster. Radio communications at high frequencies, used by aviation, by militaries, by shortwave broadcasters, and by amateur radio operators, depend on the ionosphere for long-distance propagation. Solar flares cause radio blackouts on the sun-facing side of Earth, disrupting communications across large regions, predicting space weather, providing warnings of dangerous solar events with sufficient lead time for operators to take protective action. Depends fundamentally on understanding the solar cycle. How active will the next year be? How active will the next decade be? These questions determine the risk environment for satellite missions, for astronauts, for grid operators. Polar fields at solar minimum that are the best current predictor of the next cycle's amplitude. Better polar field measurements, the kind that Solar Orbiter is now providing, translate directly into better cycle predictions, better space weather forecasts, better space weather forecasts, and better protection of the technological infrastructure that modern civilization depends on. The solar poles are not abstract astrophysics. They are the origin point of the cycle that governs the space environment of our entire solar system. Solar Orbiter approaches the question of the solar poles from one direction, observing from increasingly high latitudes with imaging and remote sensing instruments that characterize the polar surface and corona. Parker Solar Probe approaches the same question from a different direction, diving deep into the inner heliosphere, reaching closer to the Sun than any previous spacecraft, measuring the solar wind in situ at distances where its properties have evolved relatively little since leaving the solar surface. Parker Solar Probe was launched in August 2018. Primary objective is to answer the two most fundamental questions in heliophysics. Why is the corona so much hotter than the surface below it? How is the solar wind accelerated to the speeds it achieves? To answer these questions, Parker must get close, very close. At its closest approaches, it dips within approximately 6 million kilometers of the Sun's surface, closer than any previous spacecraft, well inside the orbit of Mercury. At these distances, Parker Probe is sampling the solar wind at conditions unprecedented in the history of space exploration. The wind it measures is young. It left the Sun days or weeks ago rather than months. Properties reflect the acceleration and heating processes much more directly than wind measured at Earth's orbit, which has been modified by 100 days of propagation and interaction. Among Parker Probe's most significant findings, reported in a series of papers beginning in 2019, is the ubiquity of switchbacks in the solar wind. These are sudden, sharp reversals of the magnetic field direction. The field reverses by 180 degrees and then reverses back, embedded in the flowing wind. They were observed occasionally in Ulysses data and in measurements from earlier spacecraft, but their extraordinary abundance in the inner heliosphere was not anticipated. Switchbacks are associated preferentially with the fast wind from polar coronal holes, VAOST. They appear to be launched from the solar surface and propagate outward, maintaining their identity for at least some distance before mixing with the surrounding wind. Their origin is still debated. They may be generated by reconnection events in the corona, by the interaction of convective flows with open field lines, or by velocity shear between fast and slow wind streams. The coordination between Parker Solar Probe and Solar Orbiter, observing simultaneously from different vantage points, creates an opportunity for a kind of triangulation. When Solar Orbiter images a specific region of the polar corona at a specific time, Parker Solar Probe is measuring the wind that originated from that region at that time. Two datasets can be connected to trace the properties of the wind from its solar source to its point of in situ measurement. This is called source-to-sink connectivity science, and it is a major scientific objective of the Joint Mission Strategy. The fast polar wind flowing from the polar coronal holes is one of the primary targets for this connectivity science. Tracing a specific parcel of fast polar wind from its source on the polar surface, measured by Solar Orbiter's PHI magnetograph and EUV imager, to detection by Parker Solar Probe in the inner heliosphere, is the most direct way to understand how the polar wind is structured, how it is accelerated, and what processes at the polar surface leave their imprint on the wind's properties, one of the most scientifically informative properties of the solar wind beyond its speed and magnetic field structure, is its elemental composition. The relative abundances of different elements in the solar wind carry information about the conditions in the corona where the wind was accelerated. Different acceleration processes produce different compositional signatures, and measuring those signatures in the wind allows scientists to work backward toward understanding the source. Fast polar wind is compositionally distinct from the slow equatorial wind. It has lower abundances of elements with low first ionization potential, such as iron, magnesium, and silicon, relative to elements with high first ionization potential, like oxygen and neon. This difference, known as the FIP bias, reflects the different physical conditions in the source regions. The slow wind, originating from the closed field active regions and their boundaries, shows higher FIP bias than the fast wind from open field coronal holes. Parker Solar Probe's Solar Wind Electrons, Alphas and Protons instrument, SWAP, measures the properties of the electron and proton populations in the solar wind with high cadence and good energy resolution. Its measurements of the fast polar wind, when Parker probe is in the heliolatitudes and heliocentric distances where it samples the polar wind stream, have revealed that the fast wind's properties in the inner heliosphere are broadly consistent with its origin in open-field coronal holes, but contain features that reflect the specific small-scale structure of the polar coronal hole from which it emerged. The abundances of helium relative to hydrogen in the fast wind, the helium-to-proton ratio, show variation that appears to be connected to the specific magnetic structure of the source regions of the coronal hole, where the magnetic field is more concentrated. Like the footpoints of polar plumes, produce wind with different helium ratios than regions of more diffuse open field. Solar orbiters' simultaneous imaging of the polar surface can, in principle, identify these different source regions and predict the compositional properties that Parker Solar Probe should subsequently measure. This kind of detailed, compositionally resolved connectivity science, connecting specific solar surface structures to specific in situ wind properties, is only possible because of the simultaneous operation of Solar Orbiter and Parker Solar Probe. Because Solar Orbiter's increasingly high latitude gives it a direct view of the polar source regions, represents the kind of science that neither mission could accomplish alone. We introduce the campfires, the small, ubiquitous brightening events detected by Solar Orbiter, earlier in our journey. Now, more context about the solar magnetic field and the coronal heating problem, we can appreciate their significance more fully. The corona's extreme temperature, 1 to 3 million degrees above the photosphere's 5,500 degrees, has been known for more than half a century, ever since spectroscopic measurements identified highly ionized coronal plasma. But the mechanism that heats it, that deposits enough energy in the corona to maintain these temperatures against the continuous radiative and conductive losses, has been debated for most of that time. Two broad classes of mechanism have been proposed. Wave heating involves the propagation of magneto-hydrodynamic waves from the convective zone through the chromosphere and into the corona, where they dissipate their energy as heat. Reconnection heating involves the release of energy stored in the magnetic field through small-scale reconnection events. The nanoflare hypothesis, proposed by Eugene Parker in the 1980s, holds that the corona is heated by a continuous shower of tiny reconnection events, each individually too small to detect but collectively sufficient to maintain coronal temperatures. The campfires observed by Solar Orbiter appear to be direct observational evidence of the nanoflare population. They are small, ranging from roughly a few hundred to a few thousand kilometers in spatial scale. They are short-lived. Each individual event lasts minutes to tens of minutes. They are energetically modest compared to large flares. They are numerous, distributed across the solar surface in large numbers, firing continuously. The energy released in individual campfire events is small, perhaps 10 to the power of 24 to 26 joules per event. This is many orders of magnitude less than a large flare. But the rate of campfire events, estimated from the Solar Orbiter images to be very high, means that their integrated energy contributions is significant. Whether campfires alone can explain the full energy budget of coronal heating remains a research question. But they have moved the nanoflare hypothesis from theoretical speculation to observational reality. Detection of campfires at higher latitudes, where Solar Orbiter's inclination now allows imaging of the transition from mid-latitudes toward the polar regions, reveals that this heating process is not confined to the active equatorial belt. Quiet polar corona is also permeated by small reconnection events. The mechanism that keeps the corona hot operates not just where the sun is most active, but everywhere, including above and below the polar axis. This has significance for models of the corona's global thermal structure. Polar corona, above the open field regions of coronal holes, is cooler than the equatorial corona above active regions, but it is still millions degrees. The campfires occurring within the polar coronal hole provide a heating mechanism that can maintain these temperatures even in the absence of the large active regions that dominate equatorial coronal heating. Among the genuinely unexpected findings from the Parker Solar Probe mission, relevant to the question of what sits above and below the Sun, and within the extended inner heliosphere where the polar wind flows, is the discovery of a dust-free zone in the immediate vicinity of the Sun. The inner solar system is not empty. It contains the zodiacal dust cloud, a broad disk of microscopic particles produced by comet breakups and asteroid collisions, distributed throughout the inner solar system in a flattened structure, roughly coincident with the ecliptic plane. Zodiacal dust scatters sunlight. It is visible from dark locations on Earth as the zodiacal light, faint luminous cone extending from the horizon along the ecliptic on clear nights. For decades, theorists had predicted that as you approach the Sun, the dust in the inner zodiacal cloud would be heated beyond its sublimation temperature, the temperature at which solid material converts directly to vapor, creating a dust-free zone close to the Sun where no solid particles could survive. This prediction was difficult to test from Earth, which is far from the predicted dust-free zone, but it was considered well-grounded in the physics of solid silicate and carbonaceous particles. Parker Solar Probe confirmed the existence of this dust-free zone. Its instruments detected an increasing depletion of dust signal at distances below approximately 10 solar radii, approximately 7 million kilometers from the Sun's surface. At these distances, the solar radiation is intense enough to heat even refractory silicate grains to sublimation temperatures, creating a clean region of space around the Sun. The dust-free zone extends in all directions around the Sun, including above and below the poles, creating a spherical region immediately around the star in which no solid particulate matter survives. Beyond this zone, dust becomes progressively more abundant, building to the zodiacal cloud density. The boundary of the dust-free zone is not completely sharp. It is a gradual transition, as different materials with different sublimation temperatures become depleted at different distances. The most refractory materials, silicates and carbonaceous compounds, survive to slightly closer distances than more volatile materials. Transition from the particle-rich inner zodiacal cloud to the particle-free immediate solar environment is a gradual gradient rather than a hard wall. This finding is relevant to the polar heliosphere because it characterizes the particle environment within which the fast polar wind is accelerated. The fast polar wind flows through a dust-free zone for the first few solar radii of its journey outward. A cleaner environment than the equatorial wind, which also passes through the dust-free zone near the Sun, but subsequently encounters the denser dust of the zodiacal cloud at lower, ecliptic latitudes. Solar Orbiter's journey to higher solar latitudes is not complete. Spacecraft has been progressively tilting its orbit through repeated Venus gravity assists, and the most scientifically productive phases of the mission, the highest inclination observations, are still ahead. By approximately 2025 to 2026, Solar Orbiter will reach its design maximum inclination of approximately 33 degrees, the highest solar latitude ever observed by an imaging spacecraft. From this vantage point, the polar regions will be visible at a far less oblique angle than from the ecliptic, providing the clearest views yet of the solar pole from any imaging mission. The observations at maximum inclination will coincide with the declining phase and eventual minimum of solar cycle 25. A particularly valuable timing. Watching the polar fields strengthen and clarify as the cycle descends from maximum to minimum, from the new vantage point of Solar Orbiter's elevated orbit, will provide the most complete, direct characterization of polar field evolution ever obtained. The PHI magnetograph will measure the magnetic flux distribution at the poles as the post-maximum polar fields rebuild. The EUV imager will track the development of the new polar coronal holes as the polar fields strengthen. Coronagraph will characterize the polar corona's structure as the streamers and coronal mass ejections of maximum give way to the simpler, calmer corona of minimum. This is the science Solar Orbiter was designed to do, and the coming years, as it reaches its maximum inclination and observes through the solar cycle transition, produce the most consequential polar solar data ever collected. Beyond Solar Orbiter's current trajectory, proposals exist for missions that would achieve even higher solar latitudes, potentially including a true polar solar orbit, spacecraft in a polar solar orbit, passing over both poles alternately on each revolution, would provide the most comprehensive polar coverage imaginable, observing the poles as directly as Earth's polar orbiting satellites observe the Arctic and Antarctic. Achieving a polar solar orbit requires either an enormous expenditure of propulsion energy or an extended gravity assist sequence that could take decades. Solar electric propulsion, using solar panels to power ion engines, offers a potential path to progressively higher inclinations without the propellant mass limitations of chemical rockets. Advanced solar sail concepts could use radiation pressure from the Sun itself to gradually tilt orbit toward the polar plane. These are long-term visions, but they represent the natural extension of the science that Solar Orbiter is inaugurating. The recognition that the polar regions of the Sun are scientifically fundamental, that their direct observation is enormously valuable, and that investing in the engineering required to observe them properly is worth the effort. Throughout this journey, we have touched repeatedly on the connection between solar polar science and space weather prediction. It is worth dwelling on this connection more fully, because it represents the most direct link between the abstract science of what lies above and on below the Sun, and the practical needs of a civilization that increasingly depends on technology vulnerable to solar activity. Space weather prediction is currently at a stage roughly analogous to terrestrial weather prediction 50 years ago. Better than random, missing significant events, making false alarms, and lacking the physical understanding needed to dramatically improve accuracy. The Sun presents a harder prediction problem than Earth's atmosphere in some ways. The relevant processes span scales from the microscopic reconnection events in the corona to the global magnetic field structure, and the observations are incomplete. Polar fields are the most important poorly observed component of solar prediction. Current predictions rely on polar field measurements from the ecliptic that systematically underestimate field strength due to projection effects. Solar Orbiter's direct polar measurements, showing that the fields are stronger and more complex than previously thought, will recalibrate the predictive models. Improved polar field measurements mean improved cycle amplitude predictions. Knowing whether the next solar cycle will be weak, moderate, or strong years in advance. This foreknowledge has practical value for satellite mission planning, for setting operational procedures at power grid operators, for planning the timing of high-latitude power infrastructure upgrades beyond cycle amplitude. The polar science emerging from Solar Orbiter may improve shorter-term space weather predictions as well, understanding the structure and dynamics of the fast polar wind, including the switchbacks and small-scale structures that Parker Probe is characterizing in the inner heliosphere, improves models of how the wind propagates through the heliosphere and modulates cosmic ray intensities at Earth. Cosmic ray modulation has biological effects. At high altitudes, where cosmic rays are less shielded by the atmosphere, their intensity varies with the solar cycle by factors of several. Long-duration high-altitude flights receive more radiation during solar minimum, when the heliosphere's cosmic ray shielding is weaker than during solar maximum. Understanding and predicting cosmic ray modulation is relevant to aviation radiation exposure management. Practical stakes of solar polar science are real, growing, and directly proportional to the increasing dependence of modern civilization on space-based technology. Every improvement in the physical understanding of the polar regions, every discovery about the campfires, the polar vortex, polar field structure, potentially translates, through improved models, into better space weather predictions that protect the infrastructure of modern life. There is a particular kind of scientific experience that deserves more attention than it usually receives. Not the experience of a dramatic discovery, a new planet, a confirmed signal, a particle predicted and found. The experience of seeing something clearly for the first time that was always there, always important, always theorized about, but never directly seen. This is the experience that Solar Orbiter is providing for solar polar science. Polar regions have been present since before the Earth formed. The magnetic field at the poles has been organising and reversing for as long as the solar dynamo has operated, for billions of years. Theorists have been modelling the polar field for half a century. Once indirect observations have constrained the models and produced tentative pictures of what the poles must look like. And now, for the first time, direct images, direct magnetic measurements, direct observations of the polar corona, from an angle that actually shows it without the compressive distortion of an equatorial perspective. What this experience teaches, beyond the specific scientific findings, is something about the relationship between models and reality. The models were not wrong. They captured the essential physics. The polar field reverses. Meridional flow transports flux poleward. The fast wind flows from the polar coronal holes. But the models were incomplete in ways that only direct observation could reveal. The fine-scale complexity of the polar magnetic field. The organised vortex-like circulation near the poles. The abundance of campfires at high latitudes. Detailed temporal evolution of the polar reversal. These features were not predicted, or not predicted with confidence, because the models were built without direct polar observations. They incorporated assumptions about the poles that were plausible, but not grounded in data. When the data arrived, the assumptions were partially validated and partially revised. This is the normal rhythm of science. Theory outpaces observation at the frontier. Then observation catches up and reveals what theory missed. Then theory is revised to incorporate the new observations. Then it outpaces observation again at the new frontier. The solar poles represent one of the most recent places where this rhythm has played out. A region that had been theorized for decades, finally observed, and found to be richer than the theories had fully captured. The richness is not surprising in retrospect. It is entirely consistent with the general principle that the universe, examined carefully, is always more complex and more interesting than any model. The Sun is the only star whose surface we can image in detail, atmosphere we can probe with spectral resolution, sufficient to characterize individual features, whose wind we can sample in situ, and whose magnetic cycle we can track in real time over multiple decades. This makes the Sun the most important calibration object in all of stellar astrophysics. Every model of stellar magnetism, the dynamos of other solar-type stars, the spots and cycles of K-type and M-type stars, the activity of young stars, the quiescence of old ones, is ultimately grounded in what we learn from the Sun. Polar regions are particularly important in this calibration role. The polar magnetic fields are the part of the Sun's magnetic configuration that most directly connects to the global dynamo. They are the product of the cycle and the seed of the next one, the embodiment of the memory that gives the solar dynamo its 11-year periodicity. For other stars, we observe activity cycles, variations in chromospheric emission, and in some cases stellar luminosity that indicate magnetic cycles analogous to the solar cycle. The Mount Wilson Observatory's program of chromospheric activity monitoring, running from the 1960s through the early 2000s, documented activity cycles in dozens of solar-type stars. Some show regular solar-like cycles. Some show irregular or no detectable cycles. Few show what appear to be analogues of the Maunder minimum, prolonged periods of suppressed activity. Understanding the physical origin of these different behaviours. Why some stars have regular cycles and others do not, what determines the amplitude and period of a cycle, requires understanding the solar cycle mechanism in sufficient detail to apply it to other configurations. The solar polar fields and their role in the cycle are central to this generalization. Solar orbiters' polar observations are therefore not merely solar physics. They are stellar physics. They are providing calibration data for models that will be applied to understand the activity of stars hosting exoplanets. Stars whose activity cycles affect the space weather environment of any planets they harbour, and whose stellar flares may affect the habitability of close-in rocky planets. The question of whether M-dwarf stars, the most common type around which many potentially habitable rocky planets have been found, can sustain stable, regular cycles analogous to the solar cycle, or whether they are permanently in a Maunder minimum-like state, or whether they are perpetually in a state of maximum activity, is directly relevant to the habitability of their planets, and the answer requires the kind of detailed cycle physics that Solar Orbiter is building. There is something worth dwelling on, quietly, without rushing past it, in the fact that the star we depend on most completely, the one closest to us in all the cosmos, the one whose light has driven every biological process on Earth for 4 billion years, still had, until very recently, 2 large regions that no instrument had properly seen. The Sun is not remote. It is 8 light minutes away. Radio signal takes 8 minutes to bridge the distance. We can observe its surface features with ground-based telescopes in real time, sent spacecraft to orbit it. We have measured its seismic vibrations. We have sampled its wind, yet the poles, the axis around which the entire star rotates, the origin point of the fast wind that fills the heliosphere, the seat of the magnetic memory that drives the 11-year cycle, remained in a kind of observational penumbra for centuries, because we could not see them in principle, but because our vantage point, locked in the equatorial plane by the geometry of planetary formation, made direct observation impossible with the instruments we had. This is not a story about failure. It is a story about the persistence of curiosity and the creativity of engineering. Recognizing a systematic blind spot is not the same as accepting it. The generations of solar physicists who knew the poles were important, but could not see them directly, did not simply wait. They modelled. They inferred. They built the best picture they could from the available evidence. They designed, over decades, the mission that would finally look. Solar Orbiter, progressively climbing to higher latitudes, represents the culmination of this persistence. Every gravity assist from Venus, every degree of orbital inclination gained, another step towards seeing the star we depend on as it actually is. Not the face we have always watched. The whole sphere, what is being found there, is worth the effort. Complex magnetic structure. Organized polar circulation. Ubiquitous small-scale heating events. Fast wind, carrying the seeds of its own turbulent structure from the polar surface outward through the solar system. The Sun above its equator is not what the models predicted in every detail. It is richer, more complex, more interesting, in the way that everything, examined carefully enough, turns out to be. Above the Sun's north pole, in a direction perpendicular to the plane of all the planet's orbits, pointing away from the disk of the solar system toward the galactic north, there is a stream of plasma moving outward at 700 kilometers per second. It left the polar coronal hole, that vast dark open region of the solar corona, perhaps days ago. Post. It emerged from concentrations of magnetic flux on the solar surface, accelerated by processes that are only now being directly measured, carrying within it the imprint of the specific structures from which it emerged. Polar plumes, campfire-scale reconnection events, the organised flow of the polar vortex. It moves outward through the inner heliosphere, through the dust-free zone, through the territory that Parker Solar Probe is now sampling at distances closer to the Sun than any human-made object has previously reached, carries switchbacks. Those sudden sharp magnetic field reversals that the probe has revealed to be so abundant in the young solar wind, it continues outward, this stream, past the orbit of Mercury, past Venus, past Earth, where it contributes to the solar wind that sustains the aurora and occasionally disturbs the magnetosphere. Past Mars, past Jupiter and Saturn and Uranus and Neptune. Through the outer heliosphere, decelerating through the termination shock, entering the heliosheath, and eventually, after perhaps a year of travel, it meets the heliopause, the boundary at which the Sun's influence ends, and the interstellar medium begins. There, the polar solar wind blends into the larger story of the galaxy. Its energy dissipated, its particles mixed with the interstellar plasma, its memory of the polar surface dissolved into the broader medium. The Sun continues to replace it, continuously, as it has for 4.5 billion years. The polar coronal holes stream plasma outward. New wind replacing old, the cycle continues. Poles reverse every 11 years. The fast wind alternates between north and south dominance. The campfires fire and dim and fire again across the polar surface. Solar Orbiter watches from its inclined orbit. Each Venus gravity assist has tilted its trajectory a little further from the ecliptic, a little closer to looking directly down at the poles. PHI magnetograph measures the magnetic field strength and structure. The EUV imager captures the campfires and the polar corona. The in situ instruments measure the wind properties just after it has left the corona. The data streams back to Earth, to scientists in labs in Germany, France, the United Kingdom, Spain, the United States, Japan, dozens of countries contributing to the most sophisticated solar observation program in history. The analysis proceeds. Papers are written and reviewed and published. Models are updated. Predictions are refined. And the Sun, indifferent to all of this, proceeding with the patient, enormous business of fusing hydrogen in its core and cycling its magnetic field in its outer layers, continues to be more interesting than the models predicted. There is something deeply comforting in this, in the recognition that the nearest star, the one we have been watching our entire existence, the one we understand better than any other star in the galaxy, still has things to teach us, for still has regions we are only now seeing clearly for the first time. Still surprises the people who have devoted their careers to understanding it. The universe does not run out of complexity. Not at the largest scales, not in the distant galaxies and the cosmic microwave background, not at the smallest scales, not in the quantum fluctuations and the particle physics, and not at the most familiar scale, not in the star that rises every morning, and has been rising since before there was anything on Earth to watch it. Solar poles are not alien territory. They are part of our star, part of the fire that makes our world possible. And we are learning, for the first time, what actually sits there, above and below the flame. It is more intricate than we thought, more structured, more active, more deeply connected to everything else the Sun does. The Sun, the cycle, the wind, the space weather environment of the entire solar system rewards looking. It always does. Thank you for journeying with us tonight to the hidden hemispheres of our star, for sitting with the geometry and the history and the physics of a region that has been present and important and theorized about for decades, and is only now being directly seen. For finding in the patient work of Solar Orbiter the slow climb to higher latitudes, gravity assists from Venus, the progressive unveiling of the polar corona, an expression of something genuinely admirable about the scientific enterprise. The sun turns above us, its poles stream their fast wind outward, the campfires fire across its surface. Magnetic field builds toward its next reversal, and Solar Orbiter climbs a little higher, watching